Hi, my name is Dr. Julie Whitney, and this video will be about the Plant Growth Monitor design for the Transition to Engineering program. The goal of this design was to create a device that would monitor the growing conditions and, of course, the resulting growth of plants for research. This monitor would include monitoring moisture, including adding water, light, and the resulting plant growth. The key design parameters would be a method for monitoring soil moisture, a method for adding water to dry soil using a control algorithm in MATLAB, a method for monitoring light conditions, and a vision system that would record plant growth. Multiple designs were considered for several parts of this project. The first one I'm going to talk about was the adding water to the soil. There were 4 designs considered, various ways to plug a tube or plug a container to stop the flow of water with a servo motor or let it go. We also considered tipping the container and using a hole that was just the right diameter to let surface tension control when the water went in and out, or actually turning on a valve. A decision matrix, weighing things like how easy it was to get going, how dependable it would be if it was working, left design 3, which was the tipping of the container, as a design selected for this project. Additionally, we used several design choices for monitoring the sensor, but instead of choosing one, 3 were brought along in parallel to see how they would perform, and the best solution was put into the final project. This is a quick Gantt chart of the project. It took a little over 3 months. Data gathering turned out to be one of the more significant parts because you had to allow time for the plants to grow and to collect the data with soil drying out and being wet again and drying out again. I want to discuss the mathematical modeling for 2 sections of this design. The first one was the expected moisture signal. One of the possible methods of measuring soil moisture was sticking a thermistor into the soil as a wet bulb reading and a temperature sensor on the board, the breadboard, as a dry bulb reading, and then looking at the temperature difference between them. Because the water is constantly evaporating off the soil, the thermistor should be giving a lower temperature reading than the temperature sensor up until the point where the moisture level around them is equivalent. So the way that wet bulbs and dry bulbs are usually used, you use a chart such as this one, and you look up the difference in temperature between what your wet bulb is reading and what your dry bulb is reading, and that will give you the percent relative humidity in the air. Now for our situation, it's a little bit different because we're not evaporating all of that water off of the wet bulb, and we know that the dry bulb is sitting in a relatively, well, not terribly humid, about 30% relative humidity, but not a bone dry environment either. So how big would our signal be if we set it up this way? Well, there's a limit to how well we can use a chart like this. If you look at the top axis on this chart, it's a logarithmic axis, and so it's not very easy to draw a straight line approximation on one of those and say, oh, we'll be about here. So instead, we looked at the literature to see if we could find a way to anticipate what kind of signal, at least the range of signals that we might expect to see. Found a paper that instead of using the wet bulb, used the dew point. And the dew point is the temperature at which water is going to condense out of the air. That would always be lower than the wet bulb, which was always going to be lower than the dry bulb. And this equation came from that paper for the temperature, the dew point temperature. So in this case, 70% relative humidity would give you 100% relative humidity minus the lab, the room temperature 22C times 5 divided by that dry bulb. And that would give you a dry bulb temperature of about 16 C, or about 4 degrees C, or 7.2 degrees Fahrenheit, as being the maximum difference that we would probably expect at room temperature for our system. Well, 7 degrees Fahrenheit isn't a lot of signal, but if you look at the thermistor and the temperature sensor that we have, their sensitivity was better than that, so it was likely that we were going to be able to get a good reading from our system. The other thing we wanted to model was the water delivery system. We set it up to put it in a container, draw a very small hole so that surface tension would not allow the water to drip out when it was flat. However, when you tipped it down so that the hole was down in the water level above it went up, then that hydrostatic pressure would overcome the surface tension and the water would drip out into the plant. So the key to that design was to create a hole in the container that was just the right size. It was just small enough that when the container is not tipped, the hole holds back the water with surface tension. And when it is tipped, the head pressure is increased and the water comes out, and you get most of the water out that you were looking for. So you want that parameter to be just right. So you want to calculate different hole sizes, different pressures, different volumes that you could have. So the Laplace law, which is down the middle of this slide, shows that delta pressure is equal to 2 times the surface tension divided by the radius of that hole. Now hydrostatic pressure, that's the amount of pressure that's trying to overcome, which is that delta pressure thing, that has to do with the height of the water above it. So as we tilt the container down, the water rushes over it, and you can see it would go up, and it would increase that hydrostatic pressure. And that pressure is solely a function of how high it rises. So pressure is rho GH, where rho is the density, G is gravitational constant, and H is that height. So you can put all those things in an Excel spreadsheet and now play around with different high sizes of holes and different heights of water that it would hold back. Give yourself a safety factor because you don't want it dribbling out at the wrong time. And you come across about a millimeter diameter hole, just a little bit smaller than that, is probably going to be perfect for R. And how do we find that? Well, we did a curve. We looked for, I wanted it kind of in a place where it was flattening out so it wasn't changing rapidly, that it would hold back about 1/4 cup of water, and that let most of that out when it tipped. And this was kind of the sweet spot that we found. The prototype build and data collection. The mechanical build for this project was the water distribution device that tipped the container and dripped water out onto the plant. This device is shown in this CAD model. A servo motor was used to tip the plant up on the container up on its axis and let the water increase in height over the hole and drip out on the plant. The build itself used popsicle sticks because they were readily available, didn't need any extra wood cutting other than what could be done pretty quickly with a pair of scissors or some sandpaper, glued together easily, and made a good strong structure. So they were used, and the yogurt container you can see there was the container that was used to hold the water and get the hole drilled in it to drip the water out. This is a schematic of the electronics that went with it. You can see a photoresistor at the top. That was used to collect light readings. The next down is the thermistor. That was the wet bulb in the plant soil to determine the temperature of the wet soil. Next down around is the temperature sensor. That was used to collect the dry bulb temperature. And on the other side is the servo motor that was used to tip the container should the water level in the soil not be high enough and it needed to be watered. This flow chart shows how that data collection code worked in MATLAB. The goal was to look and see whether the soil was dry and also collect general data and export it into an Excel spreadsheet. This flowchart was for the vision system because separate of the controls and taking the temperature and light data, we also took pictures of the plants, and then we had to do image processing to look and see how much those plants had grown, and this is a flowchart for that image processing. Data analysis and device performance. I mentioned at the start of this presentation that we carried 3 different soil moisture sensors forward in the design to determine which was the best. The first of these in this picture is a SparkFun soil moisture sensor for just under $7 that was hooked into like a voltage divider. The next one you can see is the dry bulb on top of the PC board, so we're looking at wet bulb versus dry bulb. And then the last one over there is a piece of felt that had 2 probes stuck in 1 millimeter apart, and they were looking just at straight up resistance. Again, they were a voltage divider in the circuit. Now, after looking at all of these over time, it was determined that the wet bulb dry bulb was probably the best sensor. The SparkFun sensor, while it gave a good reading, you can see the corrosion on one of the pins. It corroded after less than 2 days in soil, so it was not meant to be left in soil. The wet bulb, dry bulb gave higher readings than the resistance, although the resistance did perform well and could have also been used. Here's the data. The soil was mostly dry, and then this is looking at both the resistor and the wet bulb, dry bulb differences. And you can see the blue arrows are where water was added, and you can see that the reading goes back up after each of those cases. Between the second and third arrow, a little bit of water was added, but not the same normal amount, and therefore a second watering was done with the third arrow. So all methods would report soil moisture, but the wet bulb, dry bulb gave the biggest signal change and seemed a bit more reliable than the other methods. The other thing we had to do was measure plant growth. So here are images of basil growing from seeds starting at day 5, which was when they first germinated, looking up to day 14. To do the image processing, we took the images and we both pulled off the plant. That's that black and white center image where you can see what the image processing thought was plant. We also removed the height of the soil, or those brown things at the bottom of the image. That's not shown here. And then we used bounding boxes in MATLAB to find the green areas and determine the plant height that way. I also grew chives because it was a different plant. Chives took a little longer to come up, but grew much faster, more quickly. In fact, it was rather interesting. I hadn't grown chives before. They come up kind of bent over and then flip up from an L shape and spring up, so they get quite tall quite fast. Again, we use the same image processing, although because the chives were very thin plants and somewhat darker green, I had to adjust the parameters on the image processing to find them more accurately. But you can see in that last picture that the bounding boxes did indeed find the green plants. Here's a graph of the growth of the basil and the chives over a 14-day period starting from when they were first planted. What you can see is the basil came up a little bit first, but then it flattened off and didn't grow very quickly thereafter, whereas the chives came up a little bit later but grew quite quickly after that point. This is the soil monitor and water code that was written in MATLAB, and this is all of the code. It's not easy to read, but basically it goes down, it takes the data from all of the sensors, it checks to see if the soil is dry. If the soil is dry, it tips the container, drips out the water, and asks you to look the next time and see if the water is reset. Conclusions and future steps. Well, one of the things that I would do differently if I were doing this over again was I would make sure that the level of the soil was right up to the top of my container, because as the plants started to grow, they were down in the container a little bit, and I missed about the first week and a half of growth because it didn't show up over the side of the container, so my vision system couldn't capture it. Secondly, it's difficult to monitor something like this over time. I would turn my computer on every morning and get data, but it is also possible to set your computer to just turn on and collect the data. So if I had a dedicated computer for this project, I would have just set it to come on automatically, collect data, and then shut back down again. MATLAB's also capable of dashboards, and a nice extension of this project would be to move this information onto a dashboard so that the user could more easily see how things were going and make corrections as needed, since this is an experimental monitoring station. And that ends the project. Thank you very much for your attention.